So now that you've got an idea of how the differential operator works, we're going to try and simplify everything down into two rules that you can use when finding the derivatives of complicated functions. So the first rule we're going to do is the power rule. And in order to illustrate that, I'm just going to make a list of functions that we've done so far, and then try and write the derivatives of those things in order to try and deduce a pattern. So the simplest and least interesting function you could ever have is f of x equals 0. So that function, if you were to sketch it, is just a line laying on the x-axis. It's always 0. It will never be anything but 0. It's just flat. So that's the key word there, flat. This line, if you were to try and write its derivative, keeping in mind that this thing is the slope of this function, because it's flat, has a derivative of 0, right? Its slope is nothing. So the derivative of nothing is nothing. That's easy. The next least interesting function is if your function is a number. So I'm going to pick 7, just for no particular reason. 7 is a line that goes through 7 everywhere. So it doesn't matter what your x value is. The value of this function is 7. Now, if you notice, this number, or this function, is also flat. So its slope, dg dx, is also 0. Which brings us to a sort of summary here, that the derivative operator applied to any constant so that means any number, like 5 or 10 or minus 12 or pi or negative 0.3698492. It doesn't matter. If it's just a number with no x involved, then the derivative of that thing is 0. End of conversation. So you can just drop it. The next least interesting function, h, would be a line. Right? H of x equals h. Now, a line with no number in front and no numbers at the back just passes through the origin like so. Now, that line, when you go to do its slope, you know from grade 9 forwards that the slope of a line is the number that's sitting in front here, and the number that's sitting there secretly is a 1. We also ran this through the derivative operator, right? The limit as h goes to 0 of whatever. And it spat out 1 as the answer. So good, we've got that one. The next least interesting function is the parabola. And it looks something like this. Now this is the first one where the slope depends on where you are. Right? For the line, because it never curves, it's always going in the same direction. The slope of this thing was 1 everywhere, so I didn't need an x in my answer. But this one, suddenly I do. Depends on where I go. And we did this in the last section. We ran it through the differential operator the long way, and we ended up with the answer of 2x. So you can see that the fact that it depends on where you are shows up in the fact that there's still an x in this slope expression. Next one up was an x cubed. You may or may have sketched these depending on what your advanced functions class was like. It's kind of like this. And I left you to do this one in the problem sets. But when you were done, you should have found, after running x cubed through the differential operator, that the derivative of x cubed is 3x squared. And then the last one, and I promise this is the last line, jklm is a function of x is x to the 4. This one was also in your problem set. It's kind of like that. It's steeper than the parabola is, and it can look more like a W if you have more terms, but that's what the basic one looks like. When you ran x to the power 4 through your differential operator, you should have ended up with 4x cubed as your answer. So there should be a pattern forming here, and I'm going to add a few little pen marks to my list in order to get this sorted out. So first off, this x here is really x to the exponent 1. Right? So there's only one of them. And if I like, I can park an x to the exponent 0 in front of this, because there's no x's there. Anything to the exponent 0 is 1. 1 times 1 is 1. I haven't changed the answer. If I make those same changes over here, and make this an x to the 1, and I make this x to the 0s, just to indicate that there were no x's there. Do you notice that when you take the derivative of this one, the exponent ended up in front, and then the exponent dropped by 1? The exponent ended in front, and the exponent dropped by 1. The exponent ends up in front, and then drops by 1. Like, this pattern is repeating itself over and over and over again. It's even true in this layer. The exponent ends up in front, and I reduce it by 1. This one gets a little wonky, right? If I were to write this out, take the exponent, write it in front, 0, 7x, and then I have to reduce this by 1. 0 less 1 would be x to the minus 1. And look what happens. What's 0 times anything? 0, which is what I had the derivative as. So this pattern where you grab the exponent on your x and you write it in front and then reduce the exponent by 1 is called the power rule, right? You're taking the power on the x and you're dropping it in front. So without using the first principles derivative, or that limit as h goes to 0 thing, I can just try these using the pattern. So if p of x is x to the 5, then dp dx should be, write the exponent in front, keep the x, but the exponent is less by 1. There you go. If q of x is x to the 6, then dq dx should be, write the exponent in front, and then reduce the exponent by 1. Now this is a hell of a lot faster than that limit thing that we were doing before, but there's nothing wrong with it. I mean, you identified a pattern that holds for all of these polynomial type functions, and you just took advantage of it. And really, the more interesting thing in all of these functions is, now that I know what the slope is, what does that tell me about the function? So if I can just quick shortcut to this, where the interesting analysis happens, then, I mean, so be it. The faster I get through it, the more interesting applications I have time to spend on. So I'm going to erase this a little bit, and then I'm going to write it out in formal. All right, lovely. So that's the first rule we're going to be using when we do derivatives. The fact that if your function is an x with an exponent on it, then the derivative of that function is drop the exponent in front, reduce the exponent by 1. So we're going to couple that with an idea that showed up in the last video. So what if your function was a of x equals 6x squared? Well, I'm going to take my differential operator. I'm going to apply it to a. So dA by dx equals the derivative of whatever 6x squared is. Okay, now in one of the examples in the last video, we found out that a values just propagate through, that they don't actually disappear on you. So what this allows you to do net is let that 6 phase right through the operator without anything happening to it. So the derivative of 6x squared is really just 6 times the derivative of the base function. So I already know that the derivative of an x squared is going to follow the power rule. So I've got 6 here. The derivative of x squared, you take the 2, you write it in front, keep the x, reduce the exponent by 1. So my derivative here ends up being 2 times 6 is 12x. So I'm going to add up here, I'm just going to add in that a value so that we know that it's there and we know what to do with it if we see it. That if this function has an a value, then that a value just shows up in front like we've been used to. Okay, so just to get through these and show how quick this operation goes, take a new function, b of x equals 7x cubed. Okay. So if I go to take the derivative of that, I can see that this is an x to some exponent, so the power rule is going to apply. I also see that there's an a value in front, but I know that I just leave that a value alone. So the derivative of this thing would be 7, bring the 3 down, reduce the exponent by 1, the derivative of that is 21x squared. Done. It's that quick. So the stuff that you were doing in the last video is it's foundational, right? Like you have to understand why this works in order to justify being able to do it. But most of what we're going to be working on just requires you to find the derivative, and you can do it by patterning. You don't have to do the first principles derivative, which should bring a smile to your face. So that's the basics. I'm just going to clean that off because I have one more example that involves the distributive property of the derivative operator. All right. So to take the derivative of this one, I'm going to apply my derivative operator to both sides. So d by dx applied to 7x cubed minus 4x squared plus 3x plus 5. All right. Now that I have that there, the distributive property of the differential operator says I need to take it and apply it to this one, and then to this one, and then this one, and then this one, and I can do it separately because they're separated by pluses and minuses. So this thing, dc dx, is going to look like the derivative of 7x cubed minus the derivative of 4x squared plus the derivative of 3x plus the derivative of 5. Okay? So I just have to go through and apply the power rule to each of these derivatives separately, so that dc dx is going to be, drop the exponent in front, so 7 times 3x squared minus 4 2x to the 1 plus 3. Remember, this is an x to the 1, so 1 comes in front, reduce the exponent by 1, plus this thing. Now that's a constant. There's just a number. There's no x involved. So the derivative of this thing is 0. Right? You ask yourself, how is this changing? Or what's the slope of 5? 5 doesn't change. 5 doesn't have a slope. It's just flat. So it's gone. dc dx then. 7 times 3 is 21x squared minus 8x plus 3. Is x to the 0 I don't really need. So there's my derivative. Now you need to know that you can do that, but you don't need to write it down every time. If you know that this thing is distributive, you can just take the derivative of this piece, take the derivative of this piece, take it from this piece, take it from this piece, and then be done. And rip it all off in one line if you like. So I'm going to clear this off, and I'm going to give one like that a try. Alright, so taking the derivative of this thing, it's an f, so that would be df by dx. I know that the differential operator is distributive, so I see a bunch of things separated by pluses and minuses. So I know in advance that I'm going to end up taking the derivative of each of these pieces separately because they're separated by pluses and minuses. I know also that each one of these chunks is just a polynomial, right? It's x to some number. So I'm going to just use the power rule, bring the exponent in front, and multiply it by my a value. So if I know all this stuff is happening, I don't even need the intermediate lines. I can just do it all in one go. 4 times negative 6 would be negative 24. Keep the x, but drop the exponent by 1. 2 times positive 3 is positive 6. Keep the x, but drop the exponent by 1. 1 times 7 would be negative 7. Keep the x, but drop the exponent by 1. And this thing is just a constant. With no x attached, its derivative is 0. So if I'd like to use one more line just to clean it up, the derivative of this is negative 24x cubed plus 6x minus 7. I don't need to write x to the 1. I can just write x. And I don't need to write this at all if it's x to the power 0. So hopefully that's straightforward. You just need to take the exponent, park it down in front, and you do each piece separately if they're adding and subtracting. So there's some other applications of this particular rule that you maybe don't quite see quite yet, but we're going to do a few of them. So let me clean this off and we'll see how that goes. All right. Now that thing does not look like that. But if you remember some of your exponent laws from grade 11, if I have something that's in the denominator of a fraction, I can write it using negative exponent notation. So this thing, this is really x to the negative 2. And once I do that, I have converted this rational function into something that the power rule applies to. So if it looks like that, then allegedly this should work. I should be able to just take the exponent and write it in front. So dp dx should be, bring the negative 2 in front, keep the x, and drop it by 1. And you just have to be careful that negative 2 minus 1 is negative 3. And if you'd like to put that back into fraction notation, which is entirely optional and it's a matter of personal preference, this would be a negative 2 with an x cubed in the denominator. Okay. So let's give that a try. Let's see if we can do that from first principles to try and prove that that's true. So I'm trying to show that if p of x equals x to the negative 2, then dp dx is negative 2 over x cubed. So I'm going to have to erase this so that I have some space to work on, and then we'll give that a try. Okay, so I'm trying to fill into my first principles definition of a derivative, where I'm going to need p at x plus h minus p at x all over h. So if p of x equals this, then p of x plus h will be x plus h to the negative 2. So I'm going to write that in there. Now, there's also going to be a ridiculous number of fractions involved in this. So I'm going to defraction this a little bit. Instead of writing it all over h, I'm going to write it as 1 over h multiplied by this, which is perfectly valid. And then I'm going to replace this with that and this with that. And I use the fraction notation just because it's a bit easier. So I have a fraction subtract a fraction. Now you've got an algebra tool to use there. That's common denominators. So in order to get a common denominator, this piece needs to have an extra factor of x squared in this fraction. So that will make this x squared. And this fraction needs a factor of x plus h squared. That will make this x plus h squared. So I'm going to write this as one combined fraction in my next line here. So I will have x squared minus x plus h squared over x squared x plus h squared. Now, I'm going to expand this one. And I'm going to do it because I've got this x up here that doesn't have an h attached, and I'm trying to take advantage of that fact that in all the other ones we've done, the leading term and the last term ended up canceling each other out. So I'm hoping I can get an x squared from here to cancel that one and leave things with only h's in the top. This one I'm going to leave alone. Just to save myself some work, I'm going to wait and see if I even need to expand that one out. So I'm going to do just this one. dp by dx is the limit h goes to 0 of 1 over h x squared minus. So an x times an x is an x squared. X times an h times an x gives me 2 h x's. H times h is h squared. Okay. So I'm going to end up distributing this negative into here, into here, into here. And so I'm going to end up with my x squared subtract an x squared. So good, they're gone. My next line then, dp by dx is the limit as h goes to 0 of 1 over h. I have negative 2hx negative h squared, because that negative went on here and here, over x squared x plus h squared. Now, do you see I have an h in this term and an h in that term? So I'm going to take that and I'm going to factor that h out. I'm just going to write it here because there's room. I took that h out, and this is now only an h to the 1. Now look what happens in that bracket. I had this thing times h divided by h. This goes away. So in my next line, I'm left with dp by dx is the limit as h goes to 0 of minus 2x minus h over x squared x plus h squared. Now I'm going to look at this 0 here. If I put a 0 here, it would be x plus 0 squared. Well, that's just x squared. X squared times x squared is x to the 4. That's not a 0, so I'm not going to create an indeterminate form if I put this 0 in now, so I'm just going to do it. So dp by dx is equal to minus 2x minus 0 over x squared x plus 0 squared, which is negative 2x over x squared x squared, which is negative 2x over x to the 4, and an x on top and an x in bottom cancels one another, leaving minus 2 over x cubed, which is what we said it would be in the first place. So that's fun. Turns out that these rational expressions, because you can use negative exponent notation to write a fraction like this, where to go, like this, because you can do that, it means that the power rule also applies. So I don't need to do this ever again. I can just continually use the power rule against any rational expressions I come across. So I'm going to clear this off and do a couple examples of that so you can see. Okay, so I see this rational expression there, a 3 over an x to the power 5. And if I'm going to be doing the derivative, the very first thing I do to this is to write it in negative exponent form. So I have a 3 minding its own business and an x with a negative 5. Now only the x gets the negative exponent because it's the only thing in the denominator. So now that that's up there, if I go to take the derivative, dq by dx, I'm supposed to leave this number alone, bring this down in front, keep the x, and reduce it by 1, keeping in mind that negative 5 minus 1 is negative 6, giving me a derivative of negative 15 x to the negative 6. And if you want, you could write that back in fraction form if you feel more comfortable with that notation. Okay, straight up, no problem. Just one more, just for the fun of it. T as a function of x is 3 over x squared minus 6 over x to the 4. So I'm going to be using the distributive property of the differential operator. So because these things are separated by pluses or minuses, I'm just going to take the derivative of that one and then take the derivative of that one separately. I'm going to put them in negative exponent notation so it's a little easier to see what I'm working on. This is a new example. Let's clean that off. Okay, so that would be a 3 with an x to the negative 2 attached, and a negative 6 with an x to the negative 4 attached. So dt by dx will be, we'll bring this in front and multiply. Negative 2 times 3 is negative 6. Keep the x, drop it by 1. Negative 4 times negative 6 is positive 24. Keep the x, drop it by 1, and we're done. If you feel so inclined, you can put it back into fraction notation, but it isn't necessary. Negative 6 over x cubed plus 24 over x to the 5. And there you go. So the power rule is handy because it applies to polynomials, right? Power x squared, x cubed, x to the 4, etc., all the way up. It also applies to rational expressions, which are all the x's with negative exponents, x negative 1, x negative 2, x negative 3, etc. And there's one more type of function that you could write as an exponent. I'm going to clear this off and we'll try one of those. All right. So the radical, or the square root function, also can be written as a fraction. You'll have to remember back to grade 11 and to advanced functions that a radical, a square root, can be written as x to the 1/2. So if I follow my exponent, or my power rule, sorry, then the derivative of this thing should be take the exponent, write it in half, keep the x, and subtract 1. Now, 1/2 minus 1 takes you to negative 1/2. So that should be my derivative. So I'm going to try and do it longhand. I'm going to have to erase this. So maybe w equals x to the 1/2, then dw dx equals 1/2 x to the negative 1/2. I'm going to erase this. I'm going to try it with the first principles derivative to make sure that this thing that looks right actually works. All right, here we go. So I have a w to the x that I'm going to write in there, and I'm going to use radical notation for it. So w at x plus h will be the square root of x plus h. There we go. So I'm going to fill those in. Okay. Now, I need to get this x to cancel that x somehow. And the thing about radicals is you can't just reach in there and split them up into two different pieces. That breaks a whole bunch of rules. It breaks Bedmus. This thing is an exponent. You're supposed to deal with it first before you can do the adding. So you can't just peel that root h out of there. I'm going to have to use a dirty trick. And so the dirty trick is called rationalizing the numerator. It sounds like a painful experience. The root of this is your difference of squares factoring. So if I have this, all right, I'm handed that. So that's what I've got here, a thing minus a thing. If I take that and I multiply it by the same things but added instead, then I end up with a times a is a squared. A times b is ba. B times a is ba, but this time it's negative. Negative b times b is negative b squared. Look what happens to these inner terms. Plus ba minus ba goes away, and I'm left with this thing in front squared minus this thing in back squared. Now that'd be real handy, because if I could get this thing squared and that thing squared without generating a mess in the center, I wouldn't have any radicals anymore, and I could just clean this up with normal algebra. So I need this piece, this conjugate is the word for that, the thing that has the same bits but it has a different sign in the center. So the conjugate I need for this particular thing would be the first radical, x plus h, the second radical, root x, but with an addition in between. Now you can't just multiply by a thing, right? Like that's not allowed unless you put it in the denominator too. So I'm going to do that. Maybe only need one set of brackets here. So if I actually do this expansion in the numerator anyway, limit as h goes to 0, I would have root x plus h multiplying root x plus h. And then I'd have root x plus h multiplying root x. And then I'd have negative root x multiplying root x plus h. And then I'd have negative root x times positive root x, which is negative root x times root x. All over. Marker's getting tired. H, x plus h and a root plus. Now that is disgusting. However, as advertised, I have a negative root x, x plus h, and a positive root x, x plus h. These two things have eliminated each other. So when I go to write the next line, dw by dx is the limit as h goes to 0. A root x plus h times a root x plus h is a root x plus h squared. That's all gone. That's all gone. Subtract a root x multiplied by itself. Me with h root x plus h plus root x in the denominator. Okay. Now, as again previously advertised, a radical, a square root squared, actually undoes both functions. So I don't need that. And a root squared happens again. I don't need these. They've undone each other. And so what I'm left with in the numerator is x minus x, and that's gone. So in my next line, I have dw by dx is the limit as h goes to 0 of h, so that's all that's left, over h root x plus h plus root x. Okay. And with 1 in the top and 1 in the bottom, those divide each other away. Now you're not allowed to leave this empty. The thing you have to remember is that h divided by h isn't 0. H divided by h is 1. There's a 1 up there. Now that that's done and that h in the denominator has disappeared, I'm okay to use this 0 for h. X plus 0 would be root x, and a root x plus a root x is 2 root x's. Something is left behind in the denominator, so no problem. So I'm going to actually pull this limit, fill in the 0 for h. Is 1 over root x plus root x, because x plus nothing is x. That gives me 1 over 2 root x. Now, a radical x is just x to the 1/2, and an x to the 1/2 in the denominator is really just 1/2 x to the negative 1/2, which is exactly what we were expecting again. So that's really handy. This one rule, the power rule, applies to polynomials, to rationals, and to radicals. That's 3 out of the 7 basic functions. So all you need is that power rule to do almost half of the functions you'll ever work with. So keep that one in mind. Grab the exponent, pop it in front, and reduce the exponent by 1. So I'm going to clean this off. I'm going to do some examples with these radical functions, and then we'll move on to product rule. Okay, So I have a whole pile of radicals in there. I have a radical in the basement, and I have a cubed root now instead of a square root. So before I proceed, I'm going to take these radicals. I'm going to take these radicals and I'm going to put them in fraction exponent form so that I can see how my power rule is going to work. So this function is really a 4 x, and a cube root is to the 1/3. This is a -6 with an x in a square root in the denominator. It's x to the -1/2. And this is a sad, lonely, defenseless 2, which is about to get mangled up by our differential operator. So shed a tear for the 2, and then be rid of it. Okay, here we go. So dg by dx should be, keep the 4, drop the exponent in front, keep the x, and I have to subtract 1 from 1/3. So 1/3 minus 1, that's 1/3 minus 3/3. That's 1 minus 3 is -2/3. So that's what goes up here. I keep the -6, so keep a values all the time. Take this exponent, write it in front, keep the x, subtract 1 from that. So -1/2 minus 1 would be -1/2 minus 2/2, which is -3/2. And the derivative of any constant just vanishes. Alright, so I'm going to take a minute just to clean this up a little bit, because I know that fractions can cause some people heartburn, so I'm just going to show you how to handle them. So dg by dx will be 4 times 1/3 is 4/3. Easy. -6 times 1/2. Well, half of 6 is 3. And a negative times a negative is a positive. So I've got plus 3 x to the -3/2. Alright. Now, I'm going to use some exponent laws to try and put this back into fraction/radical notation. And I'm going to have to change colors because my yellow has finally expired. Okay. So dg by dx is 4/3. Now this thing, that should be in the denominator because of the negative. The way you read this is without the fraction part there, that would be x squared, right? X to the 2. But it's attached to a 1/3 here in the exponent, and that's cubed roots. So this term is 4/3 of 1 over the cube root of x squared. That's what that thing is worth. This one would be plus 3. I need a denominator because of that negative. It would be x cubed otherwise, and it has a 1/2 type fraction, so I have a square root. So altogether, if I wanted to compile these as a single fraction, 4 times 1 in the numerator, 3 times the cube root of x squared, plus 3 over the square root of x cubed. There you go. So power rule applies, and the only tricky part is trying to manage this exponent notation, and you will get better at that as you do more examples of this. Okay, so I'm going to break the video here, and I'm going to come back with a second video for product rule, just so that you don't have to forward 30 minutes into this video to find the product rule instructions.